start from home then too. Everybody. Okay. Oh, really? Okay. It's pretty bad, huh? Pea soup, as they say. Okay. Anyway, I guess I got started here. People come late. It's hopefully recorded here too, so gotta get something. Basically, I'm gonna do more of the application problems tonight. Just some more of those here. It's like section 4142 continued. So kind of more word problems, I should say. Next one we'll look at, we did one last time, population, crowding, logistic, kind of remember that from last time. Another one here, look at a little bit, is Newton's law of cooling. Okay, or it could be warming as well. So another example here. So let's say you have like an object here, like maybe a piece of metal or something, or a pizza, or whatever. Maybe a pizza or a piece of metal or some object here. Okay, you assume it has some temperature throughout, some temperature constant throughout it here, let's say. Okay, and you take this maybe out of an oven or something, and you put it in a room, say maybe at 70 degrees. So the room's like 70 degrees, for example, something like this. Okay, and Newton's law of cooling for this, it looks like this here. So dt, change in temperature with respect to change in time for this object. Okay, it's like this. It's negative K times T minus, in this case, it'd be 70. Okay, for Newton's law of cooling, where K is some constant here. Okay, so, and typically there's like a negative in front of here to get the signs right, because, yeah, like if say the temperature is really, if it's like a hot temperature, like, say 300 degrees here or something, right? You expect the temperature to drop. Basically, the idea is keep the K positive here. So if it's like big hot temperature here, right, then you expect the temperature to drop. This would be a negative number over here. If this is big number here, hot temperature, this should be going down, right? And you put it in a cool room, right? The temperature should be going down of the object. Okay, so if you put the negative in there, it keeps the K positive. But it's just the way the model is. Okay, but anyway, basically the change in temperature, the rate of change is proportional to the difference between the temperature and the surroundings. So the bigger the difference, the faster it changes the temperature, right? So, and let's say also for this one, let's say we have an initial value problem here, like T of 0 at time 0, let's say it's 300 degrees, okay? And then we also maybe know, say time 10, maybe 10 minutes later, it is, say, 150 degrees, like that. So let's say we have these values here. And then we want to find the temperature as a function of time then, like this. Basically, it means we want to solve the differential equation here, right? And then plug in these conditions and then figure stuff out. Now this equation here then, a couple ways you could do it. It's separable. I could divide this over to the other side. Okay, you could divide it over and make it separable that way. It's also a linear equation. It's a linear differential equation. If I distribute the K here, I'm going to do it that way instead. It is separable, but I'm not going to do it that way. We're going to use the fact that it's linear to get negative KT plus 70K here, like this. I distribute the K through. Okay, now move this over to the other side. So you get dt plus KT is equal to 70K. Like that. Now this is actually a linear equation here. This is like the P of X, or in this case, P of T, I guess you'd say. And then this is the F of X over here. It's just a constant function now. Okay, so really it's a linear equation here. Okay, so what's our process there? Look for solutions, right? Look for solutions like this. In this case, it'd be T. T equals some function U, right? U of little t here times e to the, it'd be negative, and then it's integral. In this case, the P of T, that's the K here. Right? So look for solutions like this, or u e to the negative kt. And then you substitute it in here. You know, you got to do your product rule here then when you substitute it in. So you get what? U prime e to the negative kt plus, and then now you keep the u and take derivative of the next one here. So what? That'd be e to the negative kt times what there? Negative k. Good. Yep. Okay. So negative k. And then plus kt. So k, and then t is this again. Okay. Equals 70k for here. And then you get the cancellation here, right? So you get that cancellation here then. So then u prime e to the negative kt is equal to 70k, like that. Now next then you multiply this, put this over near side. So on both sides by e to positive kt, okay, to move it over. So you get u prime equals 70k e to the kt. That. Okay. Anything there on that? And this is like du dt. You can move the dt over. But basically, it's just the t over here, so you just integrate it. So u would be equal to integral this. Right, so it's equal to this integral, equal to this then. So how that goes? So I guess the 70k can come out there. And then now e to the kt, what would be antiderivative of e to the kt? Yep, 1 over k e to the kt, right? Like that. And then don't forget the plus c here then on that. Okay, and then of course here then the k's cancel there, right? So you get u is equal to 70 e to the kt and then plus c, like that. So now then recall what the t was then, right? So now recall that t was equal to u e to the, was it e to the negative kt? Okay, like that. So that means then that t is equal to, that'd be e to the negative kt times 70 e to the kt plus c, or t is equal to, that would be 70 plus c e to the negative kt, like that. So that's the differential equation. We got solved there for this then. Okay, so this would be the temperature of the object as a function of time. If the ambient temperature is 70 degrees, okay, this is what it would look like then. But we have to figure out the constants here though, but that's basically the solution. Anything there so far? It's just a linear equation. So this is actually easier than the last time what we did there. Now, next thing, get the constants here. So I know then at t0, at time 0, it was what? 300, right? So 300 equals 70 plus c e to the negative k times 0. So what? 300 equals 70 plus c, because this is really 1 right here. So then c is equal to 230, I guess. So that's that. So we at t equals 70 plus 230 e to the negative kt. Okay, and then the other thing we need here then would be, let's see if that makes sense. For example, right at time 0, what's the temperature? Right, so if little t were 0, temperature would be what? At time 0? 300, right? Because this was become this is 1 right here when t is 0. So make the initial condition fits then, right? So t of 0 is 300. So that part works. Now the other thing we need to get that k, we have this other data point. Temperature at time 10 is 150. Okay, so we got 150 equals 70 plus 230 e to the negative, was it k times 10? It was 10, right? Was that 10? Yeah, times 10. Okay, thank you. And so that would be what? 80 equals 230 e to the negative 10k. So then, well, we got 80 over 230 is equal e to the negative 10k. And then take natural log of both sides. Equals, that'd be negative 10k over here. And then divide by negative 10. Right, so this would be equal to the k here then. So yeah, so the final model here then, right, we get t is equal to, that'd be 70 plus 230 e raised to the, I'll say negative 1/10. Negative 1/10. Now be careful here. Wait. I can watch my signs. Okay, it's 230 e to the negative kt. So there's actually, I guess, a negative in there. It would turn positive then, I guess, right? Like, like this here in the end, right? Because originally, right, there was a negative up here in front of the k, right? In this, there's a negative here, and then we found the k to be this with that negative there. Okay, so you got like two negatives now, right? So it becomes this right here. Okay, and I suppose they can get a maybe you guys get like a number to go here like this. If we do natural log of 80 divided by 230 and then 1/10 of it. Just to see what that is. Should be a negative something, I think. It would be like negative some number times t. A lot of negatives floating around there.
Negative 0.1056.
Okay, thanks. Like that. So yeah, so this would be temperature as a function of time then for that. Okay. Okay, so anything on that? So like right at time zero, right? At time zero it'd be 300, right? What happens as time goes on? So as time gets really big, right? At big time, like a long time after, right? This basically vanishes here. If you have e raised to big negative number, it's practically zero. Okay, so over a long time, this term vanishes here, right? This term will vanish over a long time, and then in the long run becomes 70, close to 70 then. So it becomes like the surroundings. So I guess if I were to graph it, I won't put it in Desmos, but if I did, it would go, say here's 70, right? And here's 300 to start. It would go like this. It looks something like this. It would approach 70 like that. So that's a solution curve. It looks something like that. If I put it in Desmos. So that'd be the temperature object as a function of time then, how it would cool down. According to Newton's law of cooling. So okay, anything on that? That's that one. Okay, next example, on to number 4 here. This is kind of a big one. We'll try this out. Okay. This is like a tank. So you have like maybe a tank with, say, salt, water and salt in it. Okay. So we kind of did something like this in Calc 2 way back, but something like this. But a problem like this here, let's say. You have some sort of tank here like this. Okay, and there's like liquid in here. It's water. It has salt dissolved in it. Let's say it's well mixed. Right, this is well mixed here. Okay. But it's like salt water. There's salt in it though. Water, salt in it. And let's say coming into the tank. So you have stuff coming in here. Let's say the fluid coming in has concentration 0.1 kilograms of salt per liter. Okay, and the flow rate in is 8 liters per minute. It's like that here. So that's coming into the tank. Maybe I think this is coming into the tank. Okay, and then coming out of the tank, it's well mixed. Okay, and then there's stuff coming out of the tank, say down here. Okay. Coming out of here is 6 liters per minute of liquid coming out of here. So 6 liters per minute coming out. Okay. So that's basically the idea here. Okay. And what we're looking for, let's say what we're looking for, A of T. So we're trying to say A is for amount. Amount of salt in the tank is a function of, let me just write this down here. At time T. So, okay, so let's let A of T be the amount of salt in the tank is a function of time. Here like this. And we're looking for this here, basically. What's the amount of salt in the tank is a function of time. But we need some initial conditions here. Let's say at time 0, there are 5 kilograms of salt in the tank. Okay, and there's 200 liters of solution initially in there. In other words, here at time 0, I guess at T equals 0, I should say. So given all this here, we're trying to find A of T, right? We're trying to find the amount of salt in the tank as a function of time. So it's a little tricky here, this too, because, right, you got salt coming in and salt going out because it's well mixed here. But also, too, the volume's changing because this is 8 liters a minute coming in, okay? But it's only 6 liters a minute coming out. So the tank's actually filling here too, right? So the level's going up too over time because of different flow rates here in this one. Okay, so that's what we're trying to figure out. The amount of salt in the tank is a function of time, given all this stuff here. Okay, so basically then we can write a differential equation here for this. Okay, so let's start with this here, right? We had dA dt. So that's the change in salt in the tank over time. Okay, let me make sure I got this set up right. Yeah, okay. So change in salt in tank over time. Basically, there's going to be, this is like the rate of change in salt, kilograms per minute, you know, how much salt is changing in the tank. There's salt coming in here, right? So salt coming in. So what's the flow rate of salt in? Basically here, if you multiply these together, right here, look at the units, right? That'd be, if you multiply this, what do you get for units here? If you multiply these two together and look at the units, you get 0.1 times 8, but in the units would be what then? It'd be kilograms of salt per minute because the liters would cancel when you multiply those. So the rate salt's coming in is, it's right. It would be, I'll just write like this, 0.1 times 8. That'd be like kilograms of salt per minute coming in. Okay, so this is like the rate of salt coming into the tank, right? This is like kg of salt per minute in coming into the tank would be that. Okay. And then now what's going out of the tank? So minus, now there's salt coming out of the tank. And what is that? Well, I got the flow rate out of the tank of this here, but I got to multiply it though by the concentration here of it coming out. So I guess the question is, what's the concentration of the salt here? Here I had a concentration, right? Okay, and what would be the concentration on this side? So that would be what? Would that be the kilograms of salt? So I guess the question is, what's the concentration of this stuff? Right, so what's the concentration of this stuff coming out of the tank? right? That would be the kilograms of salt divided by the volume of liquid in the tank, right? So coming out the concentration here, this would be, you'd say A, that's the salt in the tank, A kilograms, right, divided by the volume of this. So kilograms, right, the concentration of this would be kilograms per volume down here, okay, like kilograms per liter, I guess. So there's the total amount of salt in the tank. Now, what's the total volume here of liquid in the tank? It's actually a function of time. It starts at 200. See if this makes sense. 200 plus. Now, how's this changing then? The volume of liquid in the tank. Initially, it's 200. Okay, but what? It's going in at 8. It's coming out 6. So every minute, it's increasing by 2 liters. Okay, like this. Okay, so that's the concentration of the salt coming out of the liquid, of salt and liquid coming out. Right, so it's this concentration here. Actually, let me move this down a little further. Whoops, here. Right, so this is the concentration of stuff coming out of the tank. So here then, down here in the equation, okay, that'd be the concentration, which is basically the amount of salt in the tank divided by the volume of the liquid in the tank. It's well mixed. Okay, so that'd be the concentration of salt, of the concentration of salt coming out of here. And then the flow rate out is what? That's the 6 liters per minute. So it'd be times 6. Okay, so that would be the differential equation here then for it. Okay, so this is like kilograms of salt per minute out would be this one. Okay, so any questions in that part on the setup of it? So it's basically concentration times flow rate, right? Concentration times flow rate, that gives you the mass flow rate of the salt. And then over here, so the concentration in the tank times the flow rate out. You notice that, and this is changing, right? The concentration in the tank. So, okay. So now at this point then, now we get the initial condition here, right? So we got the, so what, A of 0 equals 5. So this is like our, kind of like our initial value problem here then. So this is it here then. So we can find D8, we can find A of T then from this. So. All right, so anything on that so far? Okay, so now we got to work on the differential equation here. So wait, let's clean it up a bit. dA dt equals, this is 0.8 minus, and then that'd be 6a over 200 plus 2t. I suppose you can cut it down some. Right, that'd be, I guess if you take a 2 out, that's like 3a over 100 plus t. Like that. Okay, we can get this here. Now we solve this differential equation. And this one, actually, it's not separable. Okay, so you won't be able to separate it by like multiplying, dividing things around. Okay, but actually, what kind of equation is this? So if you look at it kind of carefully, we can rewrite it a little differently. But what kind of equation is this actually? I guess your choices are linear or Bernoulli, right? So what do you think of this? Is this a linear equation or a Bernoulli? Well, actually, it'll be linear because you can take this guy here would come over. Okay, remember, so you could, right? Yeah, so it's actually, you could write like this. It's dA dt plus 3 over 100 plus t, a, like this, equals 0.8. So you can kind of twist it around and get it like this then. Okay, so it's actually a linear equation here. So, okay, so anything there so far? And then from this point, it's just like before, look for solutions, whatever look like, whatever. So we're going to look for a equals u e to the, what that be, negative integral of 3 over 100 plus t dt. Okay, like that. Okay, so a little bit tricky on this one now. So let's see. So that'd be what? U. Now the antiderivative there, what? That'd be, I could say e raised to the negative 3 natural log of, I'll say 100 plus t. We're assuming here that's not going to be negative there at all. Assuming t is greater than 0 here. Let's get that here. And then this becomes what? That'd be u. That would be what time? Is that 100 plus t raised to the negative third? Like that. Okay. If you do the exponent rule stuff there a little bit, should end up like that. Any questions in that part? I think that's right there. Okay. So then now we're looking for solutions like this. Okay. So come back across, then fill that into the differential equation here. So what we're looking for, what a equals u times 100 plus t raised to the negative third. I think I'll just leave it like that for now anyway. Okay, so look for this. So then substitute in. So then what? You get u prime times 100 plus t raised to the negative third plus then u, doing the product rule here, and then take derivative of this part. So that would be, I guess, like what? Negative 3 times 100 plus t raised to the negative fourth, like that. Okay, then that's product rule. We've got that one there. Now, plus this is 3 over, well, I'm kind of mixing up terminology, or mixing up the way I'm writing this, but 3 over 100 plus t. Then the a is this. And then equals, a lot of writing here, equals, I guess, 0.8 over here. And do these cancel here? Hopefully these cancel now. Let's see. Yeah, those should cancel, right? Because this one's on the bottom here. So it's like, if you brought it up, it'd be like negative 4 up here then. So those do cancel out. Okay, so this will cancel this. Those do go away there, actually. So we get u prime times 100 plus t to the negative third is equal to 0.8. Okay, now multiply, so move this over to the other side. So it's to the positive third on the other side. So u prime is equal to 0.8 times 100 plus t cubed, like this. Let's get that here. So then what? We get u, so u is equal to basically 0.8 times integral of 100 plus t cubed dt. Now at this point, really this is like a u substitution we do here, but you could pretty much, it's gonna be like a u cubed, right? And the du's go equal dt. So you can pretty much just kind of go for this here, I think. So antiderivative would be like this. You could do a u substitution and go through it, but it's kind of maybe not too necessary in this, because you say u equals 100 plus t, take your derivative, du equals dt. So it's become u to the third here, 1/4 u to the fourth, but the u is really this. Okay, anything in that part? Does anybody want to see the u substitution, or is that, I'm not sure. You're good. Okay, so we have that. And then, so that'd be, I guess, 0.2 there. So u equals 0.2 times 100 plus t raised to the fourth plus c. So then finally here, a is a function of time then. So a would be equal to what? It was, what was it multiplying by? It was 100 plus t to the negative third. Okay, so. Plus c here, I guess. So we got that. So then if you clean that up a little bit, take this through, that would be, it's like 0.2 times 100 plus t plus, and then c, I think I'll maybe write it back like this now, c over 100 plus t cubed. Right. So this would be the amount of salt in the tank as a function of time, like this. Okay, so anything there? Okay, now the other thing we want to get was the initial condition here. We're going to get the C up here. So then apply the initial condition. That was what, A of 0 was equal to, was it 5 or something? I can't remember what. Yeah. 5. So there's 5 kilograms of salt in there to say, okay, in the I think it was, well, yeah, 5 kilograms of salt in there. So then that was at time 0. So what we get, 5 equals 0.2. I suppose I could distribute that too, but I'll just say it like this now. 0.2 times 100, basically, plus c over 100 cubed, I guess. Kind of a messy thing here. So then what that would be, well, that's 20. Move it over, I think negative 15 equals c over 100 cubed, like this. Okay, so I get what? So c equals, that would be negative 15 times 100 cubed, basically, would be the c. $15 million. Okay. Maybe we'll just leave it. Okay, I'm just going to leave negative 15 times 100 cubed, which is fine. You can write it the other way too. But anyway, so that's the c here then. Right, so you end up with this. So a equals, and then maybe we'll finally distribute here then. So that'd be 20 plus 0.2 t plus, and then negative 15 times 100 cubed over 100 plus t cubed, like this. So that'd be amount of salt in the tank as a function of time on that. Okay, so any questions in that one? Okay, I guess it would keep increasing. It makes sense if it keeps increasing, right? Because assuming the tank, assuming the tank's really big, right? As time goes on, this is going to disappear over here, okay? Because this will disappear over here, and then, but this keeps getting bigger here as time goes on. So it'd be more and more salt in the tank over time. So now the other thing here then too, if we want the concentration is a function of time. So this is like the amount of salt is a function of time. But if you wanted this, let's say when the concentration is a function of time, concentration of salt in the tank, that'd be the basically the amount of salt in the tank divided by the volume of the liquid in the tank, right? So if we're in the concentration as a function of time, right? It'd be the amount divided by the volume. So the concentration then would be like this. It'd be this one up here. Right. And then divided by, you would divide that then by the volume, and that would be, now the volume's not too bad. That was, what's the volume as a function of time? We actually had that back up here. That was, that's this one here. This is the volume as a function of time, because it was originally 200, and then you're adding 2 liters per minute because of the difference in the flow rates. So the volume there would be that. Okay, so this would be the concentration of salt then, and there's a function of time, would be this. So, okay, and so that's how that would all work out there then. So, okay, any questions in that one? So I suppose in the long run, the concentration, if I'm thinking this right, it would be like the, basically over the long run, it would basically be like the, let's see, what would it turn into? I guess it eventually turned into like the inlet concentration, maybe. So I think as time goes on here, right, this keeps filling and filling and filling. Eventually, the stuff in here is going to look a lot like the stuff here, right? This keeps filling and going on over time, okay? Because eventually, isn't that what I think that's what would happen, right? If this keeps on going here, it's just going to turn into this stuff here over time. Okay, so if you keep filling this up here, and yeah, and that's kind of what that's what would happen down here, I think, then over time. And so, but anyway, this would be the concentration though over time though. And so, okay, anything on that? Okay, so kind of a messy one there, but there's something like that in homework where you have like a kind of a mixed, like a problem like that. Let's see here. Okay. I'm kind of curious what the graph looks like. I want to see the graph real quick. So this will probably take a couple minutes here to whatever, but I just want to see this real quick here for the concentration graph, especially. So I'll stop sharing here. Let me look on Desmos. See, www. I'll go to Desmos. Okay, and share screen here. Let's see. So the concentration one, I'll say I'll go y equals. There's a big old mess here for that. Let's see, they have it here. Yeah, so it was 20. See if this even makes sense. It looks like 20 plus 0.2 t plus this thing, negative 15 million, you said? 100 cubed. How many zeros is that? 6, 2, 3, 4, 5, 6. Okay. Divided by, say, 100 plus t cubed. That's the numerator. So that's the amount of salt in tank, function of time, divided by the volume, which is 200 plus 2t. Or no, I can't use t's here. I use x's. Remember, it does recognize that. Ooh, anything here that's interesting? I guess. Well, I don't see a lot going on there. What was the inlet concentration? It was supposed to be, maybe my time's wrong. Wait, let's see here. That's awfully flat. Let's see. Which it could be 0.1 times 8. So it's 0.8 was the inlet concentration. Okay. So let's see here. 200 plus 2x. 100 cubed. 100 is 10,000 times 100. Yeah. 100 cubed. Yeah. So that would be 6 zeros. Okay. Negative 15. Well, this must be it here, but I gotta go a long more time. Let's see. Is that really 20 there? Let's see. Yeah, 20 plus 0.2 t. Okay. Well, I'm not saying this minus out here. Does that change anything? That should be it there. That should be it. I thought I'd go to 0.8 though eventually. I was looking for it to, I thought I'd go like the inlet concentration eventually. Let's see. I don't see it. It's not going to go up anywhere, I don't think. That one. Let me zoom in here. Oh, wait. Oh, wait. Yeah, okay.
0.1 after so long.
Yeah, it'd be 0.1 after a while, right?
Yeah.
Is it? Yeah. The question is this increasing? I think it is increasing. Oh, ever so slowly. Yeah, it's just my scales. So I need more time. It's yeah. I don't know. Let's just say 0 to maybe I'll try 50. And let's say the y-axis say 0 to 0.2. Yeah, okay, there. This is getting better. Okay. Yeah, so it's increasing there. It's heading towards 0.1. Is that the inlet concentration was 0.1?
Yeah.
Is that right? Okay. Okay, that's the concentration. Right. So that makes sense. So there we go. So it's the concentration going up over time like that. Forget the negative over there, but that's what it looked like. Yeah, so, okay. Basically be approaching inlet concentration. And then the volume would keep going up though, right? If you did the volume graph, it would just go up. And so the concentration approached the inlet eventually. And so, okay, good. And so anything on that one there? Let's see. Okay. Let's see. Yeah, I don't know why I don't know. It's just a scale. It went up a lot slower than I thought it was going to. Okay, made me doubt there that think something's going on. All right. 3, 4, that's that one. Okay, got one more to go here on this. Let's try number 5. Okay, so let me switch back here. There's our screen here. Okay, so next one here. Number 5. Okay, let's say here now we got, this is like a savings account. Okay, it's a little different application here. You get the right view zoom here. Go to 200. Okay, so let's say here a savings account earns 3% annual interest compounded continuously. Initially, let's say there's $5,000 in the account. So initially $5,000 in the account. Okay. If $100 is deposited each month, estimate, I'll just write it here, A of t after t years. Okay. Now for this one here, you have to actually end up making an approximation for this, because whenever you use a differential equation to model something, it's assuming everything's continuous and nice and smooth. In this case here, it's almost like step functions in a way, because right, we're adding $100 every month, like, you know, say at the end of the month. So it's like steps up. So it doesn't work quite right for a differential equation, right? Now the interest here, compound continuously, basically that means it's compounding all the time. Like it could compound once a year at a bank, or maybe once every quarter, or once a month, or daily compounding. Okay, you take it to the extreme, it can compound every hour, can compound every minute. We're assuming continuous compounding. It compounds every instant it's compounding. That's called continuous compounding. Okay, it's like in the extreme case, basically. Okay, so it's like a limiting case there. So basically, the way this worked then, it's almost like the mixing problem we just did. Okay, it's almost like you have stuff in the tank, but it's like the stuff in the tank is generating new stuff in the tank, and then you have stuff coming into the tank. Okay, but basically here it goes like this, right? dA dt, this is the amount of stuff in the tank, or the amount of money in the account. Okay, it's equal to, now, okay, for the compounding interest part, it'd be like this. If money compounds continuously, okay, at an annual rate of 3%, this is basically the interest being generated at any time. It's 0.03a. The more money in the account, the more interest being generated. It works out like this for continuous compounding. Okay, so this is like the interest being generated at any particular time. So it's 0.03a. Okay, and this part over here then, the money flow rate in, like we're assuming $100 a month. Okay, but really the best we could really do here, assume there's $1,200 a year going into it, and it's going in continuously. It's almost like it's like dripping into the account, okay, at a rate of $1,200 a year. Okay, think of like it's this kind of, you're putting a penny in every, whatever it is, at a continuous rate to get to $1,200 a year. Okay, so it's like kind of like the flow rate into the account. Okay, so this is kind of like I think of it, it's like the money. It's like the money flow rate into the account. And that'd be like in dollars per year there. So it's kind of like the money flow rate in. Kind of like in the mixing problem before, you had the kilograms of salt per minute in. This is like the dollars per year in. Okay. Okay. So then this is how it would look like then. If you have continuous compounding, this is exact here. This is correct here. And then this is like an approximation over here. So I'll just mention this. This is an approximation. Okay, so yeah. So anything there so far on that? Oh, I'm sorry. Initially, yeah. There's our initial condition, right? So initially, there's 5,000 in the account. Okay, so this is like the model for the money in the account then. Okay. All right, so there's this then. Now, basically, all we do then solve the differential equation and get the approximation then for the money in the account. Okay, so Now, once again, you could do separation of variables here and do it that way. I like, this is actually, again, a linear equation. If you move this over to other side, right, you can say dA dt minus 0.03a is equal to, is equal to, I was going to say here, is equal to 1200. Okay, so we got this here. And now this is it's a linear equation here. Okay, so look for what here? We look for a equals u times, and then e to the negative integral negative 0.03 t or dt, or just this is u e to the 0.03 t. Like that, and then now substitute in over here, so you get u prime e to the 0.03 t plus then u e to the 0.03 t times 0.03 from chain rule, then minus 0.03, then the a here is this. Okay, then equals 1200 on this side. Okay, this here then. Now then these will cancel out, and hopefully you do. If it's going correctly, it should cancel. So let's go there. Okay, so then you get what? U prime e to the 0.03 t is equal to 1200. Okay, and then move this over, right? So then u prime is equal to 1200 e to the negative 0.03 t. So then now I just integrate here. So you get u equals, this could be 1200, and then that would be times 1 over negative 0.03 e to the negative 0.03 t. Okay, like that. So then this is u equals, and this is, I believe it's negative 40,000. This is negative 40,000 here. E to the negative 0.03 t. So that's the u then. Okay, so anything there so far on that? So then what? A is equal to, so is from back up here then. So A is equal to, that'd be the e to the 0.03 t times, oh, I forgot something here important on this. I forgot what plus c when I integrated this. There's a plus c there. Okay, so there's a plus c here on that. And yeah, so then you get this. Then distribute this through it there. So you get A equals, that'd be negative 40,000 plus C e to the 0.03 t, like that. If I distribute it through. Okay, so anything there so far? Okay, so now lastly then we applied initial condition. So now apply the initial condition. That was what? A of 0 is equal to, how much was in the account initially? It's 5,000. Okay, so 5,000. So then what we get 5,000 equals negative 40,000 plus C, because they put in 0 there, that would just drop. So that'd be 45,000, right? So 45,000 is equal to C. So it looks like what A would be equal to negative 40,000 plus 45,000 e to the 0.03 t. Okay, so that'd be approximation for the amount in the account then as a function of time. Okay, I'll go ahead and graph it here. But any questions in that? How that went? It makes sense, sort of. Because, well, it does make sense. If you put in 0 for t, put in 0, you get 5,000 initially, right? So that don't worry, the negative, don't worry about it, because if you put in 0 here, you get 5,000 to start, and then it grows from there. Okay, so let's just see kind of what that would look like. And so if I did it in Desmos here real quick and start sharing here. Okay, so see if I can get decent. This one's not quite as complicated as the other one. So if I share the screen here. Okay, so then we got y equals, it was negative 40,000 plus 45,000 e raised to the 0.03 t. That's the interest rate, was the 3%, or I'm sorry, x, let's say. And I wonder if I can reset the window. I wonder if there's a reset feature or something where I could. In fact, it should be like a default. The thing here, we could maybe home. Let's try that. That's not what I wanted. But I guess go to this again. So let's say 0 times 0. Let's say maybe 50 years or something. I don't know. This be 0. Maybe I don't know what would be like. Maybe let's see. 200,000, something like this. Okay, so yeah, there's the amount in the account, right? So if you start with $5,000 and then put in $100 a month, and assuming it earns 3% continuously all the time, okay, compound continuously to 3%. Okay, and that's not a bad even if it compounds monthly or daily, that's not a bad approximation. Then, but this would be the value of the account over time with those deposits and then the earning interest in there. You can see the power of compound interest, by the way. It goes along with, well, plus there's deposits in here too. You're depositing $100 every month. That helps too on it. But yeah, 3%, you get enough, given enough time. Compound interest, it's quite a thing. So if you're young and can put money in bank and get or in a market or somewhere get an investment return, if you're young like you guys are, you could do it when you're young. Okay, start investing or get something, get some return on it, and then you can. Yeah, savings accounts, you can get actually savings accounts for about 3% if you have enough to put in it. But it makes a difference if you're over time. So the extra 10 years in the beginning, you notice at the end, on the other end of it, a lot of people wish you would have started 10 years sooner saving money because it doubles. You can get one more doubling in there or something. It's a lot. So, okay. All right. Anyhow, so I'll go ahead and stop there.